4.2 logarithmic functions. We start with a log, and we need to know the basic parts of a log. And this a is called the base. So we would read that as log base a. And this x, we can call it the argument. And then over here, b is an exponent. It's kind of weird to think about that as being an exponent, but that's where we come up with a logarithm. A logarithm is very closely related to an exponential, all right? And in fact, I want you to kind of remember a logarithm equals the exponent, all right? So if you can remember a log equals the exponent, I think that will really, really help you out in several different types of problems. Okay, log equals the exponent. A logarithm equals the exponent. Number 1 says complete the missing equivalent forms in the table. We can go back and forth between logarithms and exponentials, and that's going to be useful for us in several problems. Our brains, for some reason, handle exponentials better. It's just easier to process an exponential, but we'll want to go back and forth at certain times, all right? But if you remember that a logarithm is equal to the exponent, it's going to be easy for you to go back and forth, all right? So notice in this exponential, the exponent is 4, all right? And this is the base. It's a base 3 and an exponent 4. So if I know that that's a base 3, I can say this is log base 3. Now write that as a subscript. Sometimes people have a hard time with how to write this, but let's go back to kindergarten when we first learned how to write. We had paper that looked like this, all right? And so if I'm writing log base 3, well, let's continue. 81 is going to be the argument, and a logarithm equals the exponent. So we can write our logarithm like that. That logarithm says pretty much the same thing as the exponential form. Now, if you're writing it, okay, if you're writing it, think about how this works. If you were in kindergarten, you'd write the word log like this. Am I the only one that saw that kind of paper when I was in kindergarten? All right. But that base 3 is a subscript, so it's going to be real small, and it's going to be down here. Everything else is on the same scale with the log. 81 equals 4. Sometimes I know people have a hard time with how big to write the numbers and stuff, but that's how it works. That 3 is a subscript. That base 3 is a subscript. All right. So same thing kind of over and over and over again. We look at this logarithm and I see a base 1/2, and I know a logarithm equals the exponent. So it's going to be 1/2 to the negative 3rd power equals 8. And that makes sense. We've dealt with those enough times to know that that is actually true. 1/2 to the negative 3rd is equal to 8. Our minds can handle that a little bit better. Next problem, we see a base 10. So this is going to be log base 10. And the exponent is 3, so that means it's going to equal a 3. Log base 10 of 1,000 equals 3. When we're talking about a logarithm, we're talking about an exponent. Next one, there's a base 5, and a logarithm equals the exponent, so that means negative 3 is the exponent, and 5 to the negative 3rd equals 1 over 125. It's just the same thing over and over. You've got a base, you've got an exponent. Okay, oops, that's the exponent, right? What am I doing? Let's start over here. You've got a base, so this is going to be log base 12. You've got an exponent, so that's what it equals. And the other 12 is the argument. Log base 12 of 12 equals 1. The next one, you've got a base 6. You've got an exponent 0, and that equals 1. And that should make sense, okay? So we can go back and forth. We can go back and forth. A logarithm, exponential, those two are very, very closely related. We can use that to solve and graph and do some other things. Number 2, solve each logarithmic equation. So this is cool because this is going to be something that you've never been able to do before. All right, we can now solve things that you couldn't before. What I always go back to when I'm solving is if there's only one variable, we should be able to isolate that variable. And I only see one variable in this problem, so I should be able to isolate it. All right. And we can use kind of the last concept. I see a base and I see an exponent. That says log base 3 of something equals 4. So what I'm going to do here, and there are other ways to do this, but what I'm going to do is I'm going to say, let's convert it to an exponential. If I've got a base 3 and an exponent 4, that's going to equal this argument. A logarithm equals the exponent after all, right? So that exponent is 4. That's a lot easier equation for our brains to handle. 3 to the 4th power is 81. 3 times 3 times 3 times 3. So I've got 81 equals 10n plus 1. We can subtract this 1 and get 80 equals 10n. And we can divide by 10. We've done this a million times. We're going to end up with n equals 8. N equals 8. We just solved an equation. Now, one thing you're going to have to be careful with is this argument must be greater than 0. All right. It has to be, and we'll talk about why here in a second, but that argument has to be greater than 0. So sometimes it's going to be necessary to check your answer. So what you would do is say, well, if I plugged in an 8, 10 times 8 plus 1, that is going to be greater than 0. So that's going to work. Sometimes you're going to find numbers that don't work. All right. That's going to be important. We'll talk about that in a little bit. So then part B, I've got a base x. I've got an exponent 2. It's going to equal 64. That's going to be a lot easier equation for me to solve. You can probably do that in your head. 8 and negative 8. Very good. So we can talk about taking the square root of both sides, plus or minus. We're going to get plus or minus 8. Part C, I've got a base 36. I've got an exponent x. Remember, the logarithm equals the exponent, right? And so I change it to an exponential just because it makes more sense to my brain. All right, it's kind of hard to deal with logarithms sometimes. But 36 to the x equals 6, and this looks like an equation you should have been able to solve in the last lesson. What you want to do, or one way to do this, is to change that 36 into a base 6. I know 36 is 6 squared, so we'd have that to the x equals 6, and I'm going to say 6 to the 1st power. Once you get that matching base, it's easy to compare because all you have to do is compare the exponents. 2x is going to equal 1, divide by 2, so x is going to equal 1/2. And that should make sense. We just found the exponent. You know, what exponent is going to make 6? 36 to the 1/2 power is equal to 6. Okay, cool. Now, before we move on, I want to kind of remind you of something that we did in the last lesson. In the last lesson, we might have had a problem that looked like 2x equals y. It's an exponential. And if we had to graph it, we're getting ready to have to graph some stuff. So let's kind of walk through what we did. If we graphed this, we might have made an xy table, and we might have picked like the number 0 for x, and then we could see, plug it in, 2 to the 0 power is 1, or we might have plugged in like a 2 or something, and 2 to the 2nd power is 4, or we might have plugged in a negative 2 or something, and 2 to the negative 2nd power, flip it, square it, you get 1/4. All right, so we knew how to graph this. We just plugged numbers in, we made a table. But I want to talk about domain and range real quick. Domain is the x numbers or potential x numbers. Basically, what numbers could I possibly plug into my table? And in this case, I can plug in 0, I can plug in 2, I can plug in negative 2, I can plug in anything I want. And so the domain for this problem was all real numbers. But then if you look at the range or the y numbers, you might be able to tell that it doesn't matter what number I plug in, I'm never going to get a negative number out. Okay, I'm never going to get a negative number. It's always going to be a positive. It's never going to be zero either. And so when we graphed it, we could tell. It's a little bit harder to tell right now, but the range of this is 0 to infinity. It's never going to equal 0. It's never going to equal a negative. It's always going to be a positive number. It might be a fraction. Even if I plugged in some negative, like -3 or whatever, it's always going to just flip it. Okay, 1 over 8. It's going to flip it and cube it, and it's a fraction. It's going to be positive, though, for sure. Now, when I graph a logarithm, if I have like log base 2 of x equals y. Logarithms and exponentials are related, but I think exponentials are easier to process. So what we're going to do is we're going to convert this into an exponential. So instead of a logarithm, I'm going to say this is a base 2, log equals an exponent, and so we're going to say 2 to the y power equals x. And so we're going to kind of do it the same way, except it's weird that your x and y have switched. And so when I do my table, I'm actually going to plug numbers in for the y here, all right? And so I might plug in 0 for y, and that's going to make x equal 1. Or I might plug in +2 for the y, and that's going to make x equal 4. Or I might plug in -2 for the y, and that's going to make x equal 1/4. And so if you notice, the x and the y's have switched, but that's exactly what inverses do, all right? These things are inverses of each other. Inverses switch x and y, and you can see x is the domain, and this time the domain has to be positive, or the x number has to be positive, and this time the range can be all real numbers. So it's a little bit weird. The range or the y can be all real numbers in this case. The domain and the range switches, but that's what inverse functions do. So we're talking about the inverse function when we're talking about a logarithm. Logarithm, exponentials, those are inverses of each other. So now, this is probably the hardest part of the lesson, I think, graphing logarithms. Give the domain and the range. So you notice on the first one, it looks like a mistake, but I actually think it's easier if you kind of don't think of it in function notation, if you think of that as a y. It's just a little bit easier to think of it as y equals instead of f of x equals, but we want to draw the graph of this. Now, in order to draw the graph of this, I think it's important to change it into an exponential. All right, logarithms hard to understand. So I see a base 1/3. And I know a logarithm is equal to the exponent. So that's an exponent y, not an exponent x. That's an exponent y. And so I'm using that same concept of a base and an exponent to change it into an exponential, just because it's a little bit easier to calculate, I think, to visualize. So if I was going to make my table, what's weird about this is you have to plug the table in backwards. All right, it's 1/3 to the y power. So when I do 0, I plug in 0 for y to figure out what x is. 1/3 to the 0 is 1. So I know I'm going to have a point at 1, 0. X is 1, y is 0. X is 1, y is 0. If I plug in +1, that's going to be 1/3 to the first is 1/3. Feel free to do that in your head if you can, but you've got 1/3 is your x, comma 1. That's going to be about right there. 1/3, comma 1. If I do +2 for my y value, that's 1/3 squared is 1/9. So I've got 1/9, comma 2. That's really hard to graph, but it's right there. One thing that's never going to happen is my x number is never going to be negative. Okay, it doesn't matter what I plug in, even if I plug in like like 5 or whatever, 1/3 to the 5th power is going to be a positive number. I think it's 1 over 243. That's something really, really small, but it's positive for sure. And so it's never going to cross that axis. It's going to flatten out to the axis basically. All right. So let's try a negative number. If we try -1, 1/3 to the negative first. Remember what a negative exponent does. It's going to flip it, right? So 1/3 to the negative first is +3. I've got x is 3, y is -1 right there. I can do -2 and say 1/3 to the negative second power, flip it and square it, and I get 9. Flip it and square it. That's 9. So 9 comma -2 is right there. And I'm out of room. I can probably draw my graph now. It's going to be flat on that axis right there, and then it's going to curve around and hit those things. Okay, that's what the graph is. All right, now I'm going to go back to something I said earlier, and I said we'd come back to it. This argument is always going to have to be greater than 0. And I kind of mentioned that in the table because I said those x numbers are always going to be positive. Those x numbers are always going to be positive. And so if you know that the x numbers are going to be positive here, we know the domain. The domain is going to be from 0 to infinity. Technically, we should draw an asymptote right there as 0, just to show that that thing is never going to cross that y-axis. All right, so what's the range? Well, the range could be anything. The range could be anything. These y numbers, I could have plugged anything I want in for those y numbers. That's all real numbers. Domain and range. Okay, so once you've seen one, they go a little bit faster because they're all pretty much the same. Next problem, I might call this a y. I just think it's going to be easier for us to handle if we think about it as a y. But if y equals log base 5 of x, I'm looking at a base 5, log equals an exponent, and so I change it to that exponential. All right. And I've still got the same, this has to be greater than 0. And so you can still, you already know there's going to be an asymptote right there at 0. At y, or at x equals 0, sorry. X equals 0, vertical asymptote. We can do our table. You just have to understand that we're plugging in numbers for y. All right, we're plugging in numbers for y. So if I do 0 for y, x is going to equal 1. So I've got the number or the point 1 comma 0. If I plug in +1, that means x is going to be 5. I've got the point 5 comma 1. If I do 2, that's going to be way too big because 5 squared, that's 25. Okay, I can do it's way over here somewhere, right? Way over this way. So maybe I shouldn't do that one. Maybe I should do -1. 5 to the negative first power, flip it, that's 1/5. So I've got the point 1/5 comma -1. 1/5 comma -1 is going to be there. Is that enough to see what's happening? Maybe. If you plugged in -2 for y, you'd have 5 to the negative second power. Flip it, square it. That's 1 over 25. It's really, really small, but it's positive. It's to the right side of the asymptote. 1 over 25th, really, really small number. That's right, basically right next to that thing, okay? I can see the curve. It's going to be flat to this asymptote. It's going to curve up, look like this, okay? It does not get flat towards that x, in that x direction, okay? So what's the domain? Well, we'll look at your x numbers. See your x numbers? Those x numbers are always going to be positive. So if your x numbers are always going to be positive, then your domain has to be from 0 to infinity. And your range, think about your y numbers. Your y numbers were not set. I could plug in anything I want for those y numbers without any issue. That's why the y numbers are going to be from negative infinity to positive infinity. So let's step it up a notch. Let's do a little bit more complicated logarithms. If I'm going to graph these things, it's basically the same idea, all right? However, this one has a shift. And you need to recognize that you've seen that kind of shifting before in other functions, in circles, in parabolas, in absolute value, in whatever. And I want you to recognize that this is a shift left 2. So what I can do is I can think about this as log base 3 of x shifted to the left 2. So ignore the shifting completely. We'll do the shift at the end. We'll move everything to the left by 2 at the end. What I'm going to do is I'm going to look at this and do exactly what we just did. So do exactly what we just did. All right. So oops, not ready to do that yet. Not ready to do that yet because it's kind of hard to do a logarithm. I want to do an exponential. I've got a base 3 equals the exponent. So 3 to the y equals x. That's going to be a lot easier. All right. So let's make a table. Notice we're plugging numbers in for y. So y is 0. Maybe you can do this in your head and get 1. Okay, now watch what I do this time. This is not technically the graph that I want. Technically, I'm drawing this graph. I'm going to shift it left. So just to remind myself that this isn't the final answer, instead of putting a point at 1, 0, I'm going to put a little bitty x. That just kind of reminds me that that's not the point. I'm going to have to shift that here in a second. All right. So you don't have to do it this way, but I kind of like doing it this way. Next, let's plug in like y equals 1. If y equals 1, then x equals 3. So I've got the point 3, 1. 3, 1 is right there. 3, 1. Can you kind of visualize what this thing's going to look like? Maybe. If I plug in 2, I'm going to have 3 squared equals 9. So I've got the point 9, 2 right there. Maybe we're out of room. Maybe we do a negative. So I do -1, 3 to the negative first. Are you guys getting good at that? 3 to the negative first is 1/3. So flip it. I've got 1/3, -1 is right there. Do you know what this graph's going to look like? Maybe we do a -2. 3 to the negative second. Flip it. Square it. That's 1/9. 1/9, -2. Got a pretty good idea what this thing looks like, right? Now, I'm not going to draw the curve because this is not the curve that I want anyway. Don't forget, we need to shift this thing to the left. We're shifting the whole thing left 2. So all I'm going to do is I'm going to take each of these x's. I'm going to go 1, 2. There's a point right there. Not on the line because the x wasn't on the line. And take this point right here, which is at 1/3, and go left 2. And again, it's not on a tick mark. It's at 1/3. Or now, I guess, -1 2/3. This one was on a tick mark. I'll go 1, 2 to the left. This one I go 1, 2 to the left. This one over here I go 1, 2 to the left. And that's going to be my curve. That's what I want. So I'm going to have this. Whoa, how'd that happen? That's going to be my curve. All right, now let's go back. Remember when I said this has to be bigger than 0? That argument in a logarithm has to be bigger than 0. It just has to. It's defined. It's like you can't have a 0 on the bottom of a fraction. You can't have negative or 0 inside of a logarithm. That's another one of our things. So if x plus 2 is greater than 0, then x must be greater than -2. If you subtract 2, right? Okay, so that does a couple of things. That shows me what my domain is. It also shows me where there's an asymptote. There's an asymptote right here at x equals -2. It's not going to equal -2. It's going to be bigger than -2. We can see our domain way up here is from -2 to infinity. That's the possible x numbers. If you look at the graph and squish it onto the x, your x numbers are covering from -2 to infinity. Your range or your y numbers could be anything. Okay, so we put a lot of stuff together there. Let's look at the next one and let's kind of do it out of order. Right now, I know x minus 3 must be bigger than 0. So if you add 3 to both sides, I can see that x is going to be bigger than 3. X is going to be bigger than 3 means I can already tell you what the domain is. The domain is going to be from 3 to infinity. We already know that. We already also know that there is going to be an asymptote right here because everything has to be bigger than 3. Anyway, let's do this. Okay, call this y. And then convert it to an exponential. I've got a base 2. I've got an exponent y. And it's going to equal x. Okay, I kind of ignore the shifting for a second. Do you see the shifting? You see how this is going to go to the right 3 and up 2? We should know how to shift. That's something that comes back in every class, algebra 2, and here it is again, all right? Right 3, up 2. Right 3, up 2. So without the shifting, it looks like this purple. It looks like this purple. And so I can do this. And I can say, well, if y is 0, then x is 1. I've got the point 1, 0 on my non-shifted. On my non-shifted, so I put an x there. If I have y is 1, then 2 to the first is 2. So I've got the point 2, 1 on my non-shifted. Let's do a negative. Let's do like -2. If I do 2 to the -2nd power, you flip it, you square it, that's 1/4. I'm going to have 1/4, -2 right there. Do you have enough of an idea of what these things are shaped like to know what this graph's going to look like? Maybe. If you don't, you can always do more points. Let's do +2. If I do 2 squared, that's 4. So I've got the point 4, 2. 4, 2 is right there. If you want to do anything bigger than that, let's do 4. No, let's do 3. 2 to the third is 8. So I've got 8, 3 right there. I've got all of those points. I know what this thing is shaped like. We've already seen 3 examples. But what we have to do with this is shift everything right 3 and up 2. So just take all your points and go right 1, 2, 3, up 2. Right 1, 2, 3, up 2. Third point, right 1, 2, 3, up 2. Fourth point, 1, 2, 3, 1, 2. 1, 2, 3, 1, 2. Going to look like this. Okay. So again, it's flat to the asymptote. Hit the dots and make that curve. We can see the domain is 3 to infinity. But again, we knew that way up here. The range is going to be all real numbers. Okay, let's switch gears. I like these problems a lot better. I think they're a lot faster. All right, but we need to know some properties of logarithms, and I made a typo on your notes, I believe. Notice this first property right here, x is greater than 0. All right, and I've already mentioned that a few times. This argument right here has to be bigger than 0. It can't equal 0, it can't be negative, it has to be bigger than 0. So make sure you fix whatever my typo was. That's going to be a 0 right there. Next property here, log base a of a equals 1. Think about an example. If I said log base 5 of 5, that equals 1. And it's kind of hard to see why that is because we're not very good at logarithms yet. Let's think about this as an exponential. If you have a base 5, a logarithm equals an exponent, so that's exponent 1, equals the argument 5. Okay, yeah, that makes sense. 5 to the first power equals 5. Yes, got it. That's what this property says as a logarithm. So then the next one, log base a of 1 equals 0. Again, that's kind of hard to understand it unless you change it to an exponential. You've got a base of some number, and a logarithm equals an exponent. A to the 0 equals the argument 1. Okay, yeah, sure. You've got an exponent 0, so of course that's going to be 1. So those three properties are some things that you should know. And then here are some other properties. These will come in handy for different types of problems. Okay. So the product property, by product property, I'm talking about product when we're multiplying those two numbers right there, x times y. Log base a of x times y is equal to log base a of x plus log base a of y. Since when we're talking about logarithms, we're talking about exponents. It's kind of like when we had this rule right here, when we had x to the third times x to the fifth. The property of exponents says that we add those exponents, and that was x to the eighth. All right. So it was like, is it multiplication or is it addition? They're kind of linked here. So when we multiply x times y, we're adding those two logarithms. So similarly, the quotient property, when we divide, that's going to be subtraction. Log base a of x minus log base a of y. And again, if you go back to something that you should already know about, if I did x to the 10th over x to the 4th, we're not really dividing those things, we're subtracting those things, and you get x to the 6th, right? It's the same exact concept. We're talking about exponents after all. So it makes sense that we're using the same properties. Then the power property, this is kind of hard to read, but that says x to the r. That says x to the r right there. Log base a of x to the r. What you've got, what's going to happen with that exponent is it's going to move around to the front. So we're going to say that equals r times log base a of x. So those three properties are useful for simplifying expressions and solving equations. When you get some complicated stuff, we can use those properties and help us with solving. Number 5 says rewrite each expression. They're wanting us to use those properties, okay? So rewrite each expression. Notice you've got a product right there. We're going to use the product property. So we can actually split that up. Log base 7 of 5 plus log base 7 of a. Make sure you leave the base 7 on there. If you don't put the base 7 on there, it is wrong. So then part B, see how that's division? We're going to use the quotient property. And the quotient property says this is going to be log base 3 of b minus log base 3 of 8. You'll like these problems because they go pretty quickly. You know these properties, it's pretty quick. All right. Part C is a little bit more complicated because we've got a couple of things going on. Notice we have the product property because you've got something times something, but we've also got these powers. And so you can do it in 2 steps if you want, but I think you're going to be able to handle doing it all in 1 step, all right, because those powers are going to come around to the front. So that first thing, I'm going to move that exponent 3 around to the front and say 3 log base 2 of a. But then since I've got a product, I'm going to add the next one, all right? And so the next one has a power of 4, right? It has an exponent of 4. Bring that 4 around to the front, and that's going to be 4 log base 2 of b. But then you've got another product, so we're going to have another addition on there. Is that b? I'm sorry? This b right here? No, that's just this argument b. Okay, good question. So then the more of these you see, the more you'll notice. The next one has an exponent 7. That 7 is going to come around to the front. Log base 2 of c. That's it. They're all kind of the same. So then the next one, I see a couple of things. I see a product, and I see a quotient, and I see some powers, right? Some powers. So take those powers and take those exponents and move them around to the front. Times, change to plus, division, changes to minus. I'm going to see 3 log base 5. There's not enough room for that. 3 log base 5 of x plus, there's no power on that, so don't move anything forward. It's just going to have a log base 5 of y. No exponent, so nothing in the front. And then that division, I can say that's minus. I've got an exponent 2, so let's put that in the front. Log base 5 of z. Don't forget your base 5. If you leave off the base 5, it's wrong. All right, there we go. Now, I think it's more useful to go the other way. Example 6 is the exact same type stuff, except now we're going the other direction. This is going to be way more useful, especially when we have to solve equations. So notice I see a minus and a plus. So I'm going to use the quotient rule for this one, and I'm going to use the product rule for this one. I can say log base 4, and you're going to have x over y times z. I think that's the best way of looking at that one. The more of these you see, the easier it will be to do. I've got this number in the front. That's going to come back here and be an exponent. I've got this subtraction, so that's going to turn into division. I'm going to see a single log base b, and then you're going to have an r to the 4th, because that's that exponent, divided by s to the 5th. Our goal here is to change it into a single logarithm. We've got a single logarithm. That's it. We've got it. And then this one, hardest one, I suppose, because of the fractions, but it's still the same kind of deal. This number in the front is going to go back there and be an exponent, as is this number in the front. It's going to go back and be an exponent. I see a plus, which is going to be the product rule. I see a minus, which is going to be the quotient rule. So let's change it to a single power of log, or a single logarithm, I mean. I've got log base a. And so that first thing is going to be an x with an exponent 1/3. And then we're going to multiply that times y with an exponent of 2/3. And then I'm going to divide that. Let's just divide by xy. And that's kind of it. But sometimes we don't like fractional exponents. So I'm just going to show you what a 1/3. This is the cube root of x. And so another way of writing that would be like this. Instead of writing x to the 1/3 power, we could write the cube root of x. That's the same thing. That's the cube root of x. That's the 1/3 power. Same thing. But since the next one is the cube root of y squared, we could just do this. That's the cube root of y squared. And so the second way is probably the more preferred way of writing the answer, but they're both pretty much the same thing.